Okay, so in chapter 14, we're going to be taking a look at the remaining functional groups that contain oxygen in them, and then we're also going to take a look at some functional groups that contain nitrogen in them. So the next one we're going to take a look at is something we've seen previously, which are the carboxylic acids. And the carboxylic acids functional group contain what's known as the carboxyl group, which has a carbonyl, which is the C double bond O, that's connected to an OH group. All right, so the collection of these atoms here makes that compound or that molecule a carboxylic acid. Sometimes you'll see that being represented in a more shortened form as COOH. Right? Both of them mean the same thing. There's the C, there's the O, there's the O, and there's the H for the carboxylic acid. So we'll take a look first of all at how we name the carboxylic acids, and what we're going to see here is a naming system that's going to be similar to what we've seen before. So in all of the nomenclature we've seen before, we first of all have to establish what the longest continuous carbon chain is, and now that carbon chain has to contain the carboxylic acid functional group. All right, so the longest chain the longest continuous carbon chain must have the carboxylic acid attached. And then what we're going to see is that the names of the carboxylic acids, they're all going to end in oic acid. All right, and we saw something similar when we looked at our alkanes, our alkenes, our alkynes, our alcohols, our aldehydes. The ending of the name actually tells you what family it belongs to. So for example, if we have a 1-carbon alkane, we would call that methane. If we turn it into a 1-carbon carboxylic acid, so there's our 1-carbon, and there's our carboxylic acid functional group, we drop the E and we replace it now with oic acid, so it becomes methanoic acid. Similarly, if we have a 2-carbon alkane, that would be ethane. To convert it to a carboxylic acid, there's our 2 carbons. There's a carboxylic acid functional group. We drop the E from the ethane. We replace it with oic acid, so it becomes ethanoic acid. So let's take a look here at a couple other examples. So here we have a slightly larger molecule. And the first thing, right, like we said, is you want to get the longest continuous carbon chain that has the carbon of the carboxylic acid as part of that chain. All right, so our longest chain here is going to be 4 carbons, and the carbon of the carboxylic acid is automatically going to be assigned position 1. All right, and then we can identify any of the other groups that are hanging off of that chain. So for instance, here we see that we have a 1, 2, 3, 4 carbon carboxylic acid. All right, so that would make it a butane if it were a 4-carbon alkane. We drop the E, we replace it with oic acid, so it becomes butanoic acid. All right, and then the numbering is locked in place because the carbon of the carboxylic acid is number 1. So when we look at our substituents hanging off of our longest chain, we see there's a methyl here on carbon 3. Okay, so we insert that as the first part of the name. So it becomes 3-methyl butanoic acid. All right, and that tells you everything you need to know about that molecule because it's systematic following the IUPAC nomenclature. Similarly, we saw that when you have a benzene ring attached to a carboxylic acid, right, we said that there's a special name that we give to that. We call it benzoic acid. And what that means is the carbon of the of the benzene ring that is attached to the carboxylic acid, that is going to be automatically now position number 1. All right, we said that when you have a ring structure and you only have one thing attached to it, that position has to be number 1. So if we have a molecule that looks like this down here, all right, you have to recognize that you do have benzene attached to a carboxylic acid, so that would be your benzoic acid. Which means this carbon here has to be carbon 1. And then if we see any other groups hanging off of the ring, in this case, we have a chlorine and another chlorine, so that would give us a dichloro. All right, then we need to number that ring to give the lowest number possible to those substituents. So in this case, we want to number the ring going clockwise, right? So if this is carbon 1 over here, this will be 2, and that's 3. So we have a 2,3 dichloro, and then we insert that in front. So 2,3 dichloro benzoic acid. All right, so again, the naming system is systematic. We're going to follow these rules, and they're the same rules that we saw ever since we started our organic chemistry. So in addition to the IUPAC names, the systematic names that we are going to preferably or preferentially use, there are also some common names that are associated, especially with some of the smaller carboxylic acids. So for instance, a 1-carbon carboxylic acid is methanoic acid. That is commonly known as formic acid. A 2-carbon carboxylic acid is ethanoic acid. That is commonly known as acetic acid. And then we have a couple other ones. Propanoic is commonly known as propionic acid. And then butanoic is also known as butyric acid, right? So you'll see those terms being used interchangeably. In terms of where you would see these, so formic acid or methanoic acid is a 1-carbon carboxylic acid. This is found in the in ant stings, when you get stung by an ant, right? That's the compound that they inject into you. And then our 2-carbon carboxylic acid here, this is ethanoic acid or acetic acid, and this is found in vinegar, right? Your vinegar is just a dilute solution of acetic acid. All right, so let's take a look at a couple examples of nomenclature, and again, we're going to preferentially use the IUPAC naming system. All right, so we have here our line angle formula. Here is our carboxylic acid. This has to be carbon 1, so then we'll get the longest chain 2, 3, 4, 5. All right, so that would give us then a pentane. For an alkane, to convert it to the carboxylic acid, we drop the E, we replace it with oic acid, so it's pentanoic acid. And then we see there's a methyl group on carbon 2, so this would be 2-methyl pentanoic acid. All right, let's take a look at another one. We'll do B down here. All right, so here we see our benzene with carboxylic acid attached. Right, so that entire thing is known as benzoic acid, which means this carbon here is carbon 1. And then you'll notice that we have a bromine attached to that ring as well. So to give the lowest number possible to that bromine, we'd want to number our ring going clockwise this way. So this will be 2, and that'll be 3. So we have a 3-bromo benzoic acid as the name for that molecule. All right, and let's go in the other direction. Let's say we're given the name, and we want to come up with a structure for this, right? Again, you want to approach this starting with the last name. So we have a hexanoic acid, so that means 6 carbons. Carboxylic acid. All right, so 1, 2, 3, 4, 5, 6. and I have my carboxylic acid functional group. I'm going to number this so that I know where everything is. All right, so the carbon here of the carbonyl, right, that has to be carbon 1. And then we have now a chlorine on carbon 4. So there's carbon 4, and I have a Cl attached to it. And that's it. All right, that's how you would draw your molecule 4-chlorohexanoic acid. Okay, so now we're going to take a look at some of the properties, both chemical and physical properties of the carboxylic acids. And the first thing we want to take a look at is their polarity, right? And what we'll see is that the carboxylic acids are going to be strongly polar because they actually have not just one, but they have 2 polar groups as part of the functional group, right? We have that hydroxyl, that OH, which is over here. We know that OH bond is a polar bond, where the O is going to be slightly negative and the H then is going to be slightly positive. But we also have the carbonyl, which we've seen before, the C double bond O, and that is also a polar bond, right? Where the O is going to be slightly negative, and then that means the C is going to be slightly positive. So we actually have 2 polar groups in the carboxylic acid, which makes it a highly polar functional group. And what that means then is that we're going to see the carboxylic acids, because they have hydrogen attached to an oxygen, they can actually form hydrogen bonds with water molecules. And generally what we're going to see is that small carboxylic acids are very soluble in water. And as the carboxylic acids get bigger and bigger and bigger, we're going to see their solubility in water decrease, right? So the trend there is, as the size of the carboxylic acid increases, the solubility in water decreases, right? And we saw that trend back in the alcohols and the aldehydes chapter as well. It's the same exact trend that we're going to see here. And the reason for it is, as the size increases, the number of carbons and H's increases, and what that leads to is the molecule then ends up becoming more nonpolar. Right, and remember, like dissolves like. So the more nonpolar it is, the less soluble it is going to be in a polar solvent like water. So if we take a look here at increasing size, going from methanoic, 1 carbon, ethanoic, 2 carbons, propanoic, 3 carbons, butanoic, 4 carbons, all the way down to 6 carbons hexanoic acid and 7 carbons in benzoic acid, we're going to see the solubility tends to decrease. Increasing size leads to a decrease in solubility. Right, and specifically here, we're looking at a decrease in water solubility. Right, so that's a general trend. We've seen that trend before. In terms of some of the chemical properties of carboxylic acids, well, that really is maybe not as obvious, or maybe is obvious. Carboxylic acids, according to their name, are acids. Right, and specifically, they're going to function as weak acids. And what that means, if you remember from our acids and bases chapter, is that they do not ionize or dissociate completely. But they do to a small extent. All right, and what that means is that in in solution, in aqueous solution in water, what we're going to see is that the carboxylic acid will act like an acid. So for instance, if I have my ethanoic acid down here, it can lose or donate that H+, which is what acids do, right? And what's going to accept that H+ is going to be the water. All right, and then the other thing you'll see here in your equation is the arrow, right? The double-headed arrow tells you that we're dealing with an equilibrium system. Specifically, we're dealing with a weak acid in this case. So if we take away an H+ from our carboxylic acid, right, we're going to end up with an anion, something with a negative charge, and we call that the carboxylate ion. That's a general name for it, and specifically the ethanoic acid becomes ethanoate. Right, so this OATE ending here tells us that we actually have an ion present instead of the neutral molecule. And then we're going to stick now an H+ onto the H2O to make the hydronium ion. Whoops. All right, so we have incomplete dissociation because the carboxylic acid is a weak acid. And again, our arrow here tells us that we're dealing with a weak acid. So we can practice that here. Let's write a balanced equation for the dissociation of butanoic acid in water, and we're going to identify the carboxylate ion. So butanoic acid is 4 carbons. All right, so but, so 1, 2, 3, 4. And in water, so plus H2O. All right, we have our double-headed arrow, and the butanoic acid here is going to act as an acid. It's going to donate this H+. That H+ is eventually going to end up on the oxygen in H2O. So our product now is going to have 1, 2, 3, 4. We haven't changed the number of carbons, but now we've taken away an H+ from it. So we end up with the carboxylate ion, which we call butanoic acid. Now we're going to change the ending. It becomes butanoate. And then don't forget that we also produce the H3O+ as the water gains a proton. All right, and that's how your carboxylic acids are going to exist in solution, right? They actually exist as the carboxylate ion. So what can happen then is if you have a carboxylic acid, it can react with a base, right? And we've seen acid-base reactions before. So I'm going to say recall that an acid and a base react together to produce a salt and water. And we call those neutralization reactions back in chapter 10. So if we take a carboxylic acid like methanoic acid and react it with a base like sodium hydroxide, right, what can happen here is the acid can donate that H+, and it can combine with the hydroxide from the base. So these two things end up combining to make water. And then we end up just sticking together now the Na+ ion from the base, the sodium ion in this case, with the carboxylate ion from the carboxylic acid, and we end up with this as our product, right? So that's known as a salt, which we've seen before, and specifically it's a salt of the carboxylic acid. So in this case, we would call it sodium, because that's our positive ion that we have, and then the negative ion here would be the carboxylate ion, which in this case is methanoate, right? So our product here, as you would name any ionic compound, would be sodium cation first, and the anion methanoate second. These are very commonly used. These carboxylate salts are used quite commonly as preservatives and also as flavor enhancers. So for instance, you may have heard of MSG, monosodium glutamate. That's actually used quite commonly in cooking. That's a flavor enhancer. And you see also these salts used as preservatives to enhance or increase the shelf life of stuff that you eat and drink. We'll take a look at a couple of these here in a second. All right, so the way that we name the carboxylate, the carboxylic acid salt, again, we're going to drop the ic acid. We're going to replace it with the 8, right? So benzoic acid here. If it reacts with a base like sodium hydroxide, again, the H and the OH are going to combine. These two combine to make water. And then the K, the potassium ion, goes with the carboxylate ion, which would be the benzoate ion, to make potassium benzoate, right? So benzoic acid here, when it loses that H+, all right, we drop the ic acid, and we change it to the ATE, that's the negative ion. And then we're adding to this, or what's sticking onto that, is the potassium ion from the potassium hydroxide. All right, that's a very, very common reaction that the carboxylic acids are going to undergo. These carboxylic acid salts, they are salts, right? As you probably know, a salt is an ionic compound. So we have positive and negative ions. And those strong attractive forces are the ionic bonds between them. These tend to be solids at room temperature, which means that they have high melting points. And because they're salts, they tend to be soluble in water. All right, so here are some examples. We mentioned a couple of these before. So for instance, the monosodium glutamate that I mentioned, or MSG, is added to enhance the flavor of different things that you eat and drink. A couple of other ones that are used for enhancing shelf life, like sodium benzoate, that's shown up here. And then sodium propionate or sodium propanoate is also used to enhance the shelf life of cheeses and different types of breads. All right, so when you look on the ingredient list on lots of things that you eat and drink, you'll actually see several of these names that sound similar to these. Those are usually used as enhancers, flavor enhancers, or to enhance the shelf life of your different products, different food products. All right, so let's take a look at an example. We have here, we want to write the balanced chemical equation for the reaction of propanoic acid with NaOH. So propanoic acid, 3 carbons, 1, 2, 3. Let me draw that a little bit better. 1, 2, 3. There's my 3-carbon carboxylic acid. We're reacting it with sodium hydroxide, NaOH. All right, so again here, the H from the carboxylic acid and the OH from the base are going to combine, and then the sodium will combine with the carboxylate ion. All right, so we remove an H+ from the carboxylic acid, we replace it with the Na, and then we also get our H2O as the product. All right, so if we were to name these things, right, we have our propanoic acid, we have our sodium hydroxide, so our product here then ends up being sodium, and then we have the carboxylate, which is sodium propanoate, and then obviously we get water as our other product. Remember here, this is our salt, so you have the sodium ion and the propanoate ion.